This is the second video for Chapter 16 in the McGraw-Hill chemistry text, and we are going to talk a little bit more about reaction rates today. So about probably 3/4 of the problems that you have with reaction rates, you're going to need to write a rate law. So it's an important skill, and it's not hard at all, because whenever you hear the word rate law, then you need to write rate equals K and then a set of brackets for each reactant. Think about it again. Think about that and make sure you got it up here, that you write rate equals K. K is a constant. It's just a letter that we use to stand for a constant that is the same for the same reaction all the time. So like lighting the hydrogen balloon, hydrogen oxygen, boom. You go look that up. There is a K value for that reaction. And we're going to solve for K eventually, but you could also look it up because it is a constant value at a certain temperature all the time. It's the same value. That's why we call it a constant. And you multiply K times the molarity of the two reactants. Remember, we don't have to worry about products, because if we know how fast the reactants are disappearing, we know how fast the products are appearing. And there's one more step, and that is that you use the coefficient, the number in front in a balanced equation, as the power for the reactant that it appears in front of. Okay, now that's a lot. You might want to rewind it and kind of play that through and make sure you understand. But we're going to use it several times now, so you'll get a chance to see that in action. And it would be a good idea for you to have the notes. I know there's a little glare on the screen all the time, and it could do probably better if we had the lights out, but then you wouldn't be able to see the board as well. So print the notes off. You can kind of see what page they're on, and then you'll have the set of notes right in front of you, and you can actually write on them. Stop, rewind, pause, do what you need in order to get each concept. So rate laws are written where we have a reaction A plus B yield C, okay, just a standard little reaction. We also have numbers in front of, like 2H2 plus 1O2. So when we have those numbers, and of course I've used the A and B type format here, we're going to write that reaction. We'll write it in terms of letters, and then we'll write a real reaction so you can see it. So here is A plus B yields C. The little a in front of the A and the little b in front of the B and the little c in front of the C tells us the coefficient. In other words, if it were 2H2, the H2 would be the A, the big capital letter, that's the stuff, and the 2 would be the little letter, which is the coefficient. Okay, so how do we write those? Two reactants. So remember, first thing, you see rate law, you write rate equals K. Start all of them like that. Now we put the number of brackets, two of them, because there's two reactants, A and B, and we raise it to the power of the coefficient. A goes in here and B goes in there. That's our rate law. Let's do one with some real chemicals. You've seen the hydrogen explosion, the hydrogen balloon explosion. We do that as a demo early in the year. So let's use that one, 2H2 plus 1O2. Okay, and if there's not a number there, don't say there's none, say there's one. One is understood, yields 2H2O. That's why this reaction is so amazing, in that eventually we'll have electricity and hydrogen for our two fuels. We'll stumble around with different things here and there, but electricity can be made clean in any way. And we've talked in class about how we have a type of a cable in the road, and our transducer will drop down and we'll run on electricity, but that's another chapter. So the H2 and the O2, two reactants, so we write rate equals K, two brackets. The H2 goes in one, not 2H2, but H2. The O2 goes in the other one. There's a 1 in front of the O2, so a 1 as its power. 2 goes up on the H2, and we call that the order. The exponent is the order. So now you've written your rate law. And then I'll ask the next question on the review, the quiz, and the test. what's the order of hydrogen? And you look up and say, oh, there's a 2 there, so it's second order. What's the order of the reactant oxygen? It's a 1. What that means is that hydrogen has more of effect if we add more hydrogen than if we add more oxygen, because it's a second order reactant. And the higher the order, the more it speeds up the reactant. Because it counts like twice, H times H, H2 times H2. So now that would be our rate law with the orders. The overall order would be the 2 orders added together. If there's 3 orders, you add them together. In this case, it's third order overall. You've got one on your review like that. You should maybe stop and work through that and make sure that you're up to speed with that. There's also some practices on that practice page. Would be a good idea for you to run through some of those. So there's a good rate law, and we've gone over all this. The overall order equals the total of the superscripts added together, and so we'll move on. So this is one of the harder things for some people. Some people catch it quick and some don't. And like everything else in chemistry, it's hard until it's easy. And I've seen so many times where somebody will just be like, "I don't get that." And then we'll go over it a little different way, and all of a sudden you see, oh, that's so easy. I get it. So this is easy. But, you know, remember, it's hard until it's easy. So if you have to rewind this or pause and maybe work through some examples, do that. So the first step here would be for us to write a rate law as much as we can. Remember, you know, most every problem that we do here we're going to write as a rate law. So what we see here is we have 2 reactants, NO and H2. Okay, those are our 2 reactants. So we know we could write rate equals K times 2 brackets, NO and H2. And we don't put the coefficients in front. We don't really know what the coefficients are yet, but we just put the compound and the subnumbers, but no big number in front. Now we've got to find out what is the order, and we're going to find the order from experimental data. So you will have usually 2 of these. Sometimes you could have 3 ingredients, but it's the same idea as 2. So if you understand how to do 1 or 2, you could do 1 with 3. Is that these are like experiments. First, second, third, fifth. I think on the 4th one he might have spilled it or something, so we didn't have a 4th experiment. And what you remember from experiments from as early as 3rd or 4th grade, maybe 5th grade, is that you don't change more than one variable. You try to keep everything constant and change one thing. So like if we had some type of new algae that we weren't sure about and we were going to test it, we'd put it in the fridge, turn out the fridge light, and water it with orange juice all at the same time. Whoa, that would really mess things up. A week later, they're dead. Was it the acid in the orange juice? Was it the light being out? Was it too cold? See, you don't know. One variable changes. And that's how you do good science. So here's the first experiment. Here's the second. So what we have to look for, and this is real key, is look for here we have a constant that H2 stays 0.004 and 0.004. So you have to ask yourself, keeping that constant, would that change the rate? No, it wouldn't. So when we keep that constant, cover this column. Now we've got a 1-column problem, which is a lot easier to work with. So let's look at this column. Okay, now we've got a rate law, and we've already said, let's get rid of the hydrogen. So let's get rid of the hydrogen, and we can get rid of the K because we're going to do experiment 1 and 2, and we say rate equals K and NO concentration. K's constant. It goes away. It doesn't affect it if it doesn't change. So we get rid of the K, we get rid of the H. Now we're focused on this one thing. And what we want to do is we want to raise it to the first power, first order, and see, is that result an example of first order? Or is that result an example of second or third order? And you probably won't have any higher than 4th order, but you know, it's the same pattern. You should be able to figure it out. So here's how we do that. We're going to substitute the first experiment, 0.001, and the second experiment, 0.002. that should be clear to you that that doubled. So when the reactant doubled with an exponent of 1, first order, what is the result in rate? So 0.001 to the 1 is 0.001, right? And that's the rate. And it's in molarity per second. The brackets mean molarity, so we could just do that per second. 0.002 to the 1, 0.002 molarity per second. So you're going to look right away and say, well, first order is always going to not change. Whatever happens to our concentration happens to our rate. And you can recognize that real easy. So first order, we really don't even have to do this. If we look at the concentration and it doubles and the rate doubles, well, then it's first order. If it doesn't, guess what? It's not first order. It's second order or third. And that's how we do this. So first of all, we doubled this, that doubled. Let's go look at our result. Well, when we doubled the amount, it went from 002 to 008. That quadrupled. So what do we know it's not? Not first order. All we have to do now is change the exponent. First experiment, second experiment, this time with a 2 as the exponent because that's second order. And now we could see, okay, well, that's 0.001 times 0.001. And when we do the math on that, we find out that we have 0.00001. I think that's right, doing the calculator in my head. And when we do this, we got 0.00004. What happened to the rate? It increased by a factor of 4. So, always, when you double a second order, it increases by a factor of 4. What was it that happened over here? We doubled, and it increased by a factor of 4. So what do we know the order of NO is? NO is second order. And if you didn't get that, rewind it and kind of go through this and maybe work some of those sample problems to make it sink in. But basically, we are changing the exponent, first experiment, second experiment, and we have to look for somewhere where the second column or the other column is constant, to where we could cancel it and cover that column. And then it's just a pattern of looking at if we double, it quadruples. If we double, it increases by a factor of 16, which would be a whole different situation. Okay? Now, it's not always just going to double, because if it did, then you could memorize 2 or 3 things. And, in academic chemistry, I usually teach that so that we get the basic concept down. Pre-AP, we're going to take that step further. So it might triple. Let's do an example of tripling. If we did 0.003 to 0.001 to 0.003, now it increased by a factor of 9. So tripling with a power of 2 went from 1 to 9. 0.001, it's going to be 0.001, 0.009. Increased by a factor of 9. So you'll get some different practices so that you get to try that. You could actually go online. There's some YouTubes and some things that go over this if you need that to help you get the concept. So that's how we figure out what the order is. Do the same thing for the other chemical, for the H2, and you look and see, oh, well, in this example, the 004 and 004 on 3 and 5 are held constant for NO. This doubles, that doubles. You know what that is already. That should be familiar to you. When one doubles, the other doubles, that is first order. So the H2 is first order. So now what do we do to our rate law? Well, we say that rate equals K times NO times H2 and we know that NO is second order and H2 is first. If we had to write the equation now, we can kind of work backwards. What are our two reactants? NO plus H2. And we don't even have to worry about the product for right now. but we do know that if there's a 2 here, that came from in front of the NO, and the 1 came from over here. And you'll get a chance to write some reactions like that, and you just have to look at what the reactants are and make your best guess if it's not a familiar reaction to what the product would be. But you can see how you can work both directions on that. And there's one on your review that's a little bit easier problem. It's NO2 plus O, and you just have, or no, NO plus O2, and you just have to figure out that we're adding one more O to the nitrogen monoxide. So you got some practices like that. Go through, maybe rewind if you need to look at it again and listen to some of the concepts again. But the main thing is know how to write your rate law from this, because the rate law is kind of the connector, the glue with all these different things. So we'll move on, and next, reaction rates and reaction mechanisms. So one of the keys here, there are 2 different ways that you're going to see reaction mechanisms. One of them is like Hess's law in the last chapter, where you add 2 subreactions or elementary reactions to get a complex reaction. That's what we call the reaction that is the kind of the total. And it's the same rule as last chapter. You take the 2 subreactions, everything on the left goes on the left of the final answer, everything on the right goes on the right, unless, remember, if we make 2 dozen and we eat 1 dozen on the way, we have to take it away over here because we produced it, but then we ate it. So we have to cross out anything that's on the right and the left. If we made it and then used it right away, we cross it out. Then we total everything. Everything on the left goes on the left. Everything on the right goes on the right, and you get your total. We did that in last chapter for Hess's law. There are some examples like that in the practice, and we'll look at another one like that. So instantaneous rate, I'll ask you to solve that. How do we solve it? Write a rate law. Rate equals K, and we'll use the one we just had, NO squared and H2 to the 1. Now you go look at that chart again, and if you look at the chart, and we'll back it up just a second here. So we look at the chart, and we know on the first line that we had 0.001 for NO, and we had 0.004, and at the same time, our rate was 0.002 molarity per second. Well, we got that, and that. Can we solve for K? You bet. All we have to do is do a little algebra. Easy now if you want to do your algebra, or you could Anderson swap these 2 down. You get 0.001 squared and 0.004 to the 1. And remember, because you could cross multiply, and cross multiplication is we can put this up here, we can put it down there. You can do 2 times 3 and 3 times 2. Doesn't matter either way. So we're just shifting to this other side diagonally, and that's the Anderson swap. Come in if you need help with that. I've got some of that early in the year if you missed that. So now we've swapped that down, or you could cross multiply in order to get that down. Remember, this is 0.002 over 1, and this is over 1, so you could cross multiply, and you get the same result. So, when I teach the Anderson swap, I make sure you understand that your basics, the cross multiplying, that's important. So here we go. Now we got 0.002 divided by 0.001 divided by 0.001 divided by 0.004. If it's on the bottom, hit the divided by key. Since it's squared, we have to divide twice on the 0.001. We get our K. Now that you know your K value, you don't even have to go look it up. Now you could use that in a rate law. Rate equals K times NO times H2, 2 and 1. And we could plug any number in here, our K value, and we could solve what's the rate going to be. So that gives you a lot of power. Notice that we're using the rate law to solve all of these. So on your review, it's going to ask you to do some of that. And on some of the practice problems, there's several that it allows you to try those, and it gives you the answer so you can always check yourself. So make sure that you're able to do that. There's not a tremendous amount of math in this chapter, but most all of it involves rate laws. Okay, so we're going to jump back up. This second screen talks about slope. I want you to be able to look at any graph and tell me what the slope represents. So if I had miles and hours here, and I had a slope, and I would always have to have a title, so car, oops, gave it away. You can't see that on the screen probably. So then I'll ask you, what does the slope of this line represent? Think of rise over run. Rise is y, over run is x, miles per hour. Well, you know what miles per hour is. That's speed or velocity. Okay, so be able to look at a graph and analyze it. In the case of this chapter, we're going to have not miles per hour, but molarity per second. And M, big M over second, you should recognize that as being one of those units for reaction rate. So the slope, that dot and that dot, we can analyze those two dots. This would be the delta x, and that would be the delta y, the rise and the run, and we could figure out what the slope was, and now we know the reaction rate just by looking at the slope. Even if it's not a perfect line, we could draw a best fit line in our data, which is just kind of like the line that evenly splits the data. All right, so move on. Reaction mechanisms. So one of the types of reaction mechanism is a diagram like this. It tells us a lot about the reaction. Every hump represents a subreaction, which we call elementary reactions. In between the humps, those in between, we call these intermediates. It's kind of like making cookies, okay? Here's all the stuff, the sugar, the milk, the Crisco, and the eggs, and over here are the cookies. But when we mix all that stuff together, we've got a goulash. That's not a product. That's kind of our intermediate. That's first step. We mix it together. Now, we put it into little stirred up, put it in little patties or little shapes, and that's not our product, although we eat a lot of those. I do, have to confess. That's not the final product. Then we put it in the oven and let it sit for 20 minutes and then let them cool. And sometimes we don't let them cool. That's your product. That's cookies. Each of these other were intermediates. They were kind of intermediate products that we have to go through in order to get to the cookies. So intermediate products, we call them intermediates. Up at the top, we call these activated complex. That would be where we're mixing all the stuff, kind of like where the mix master is going in. It's making all the goulash, the cookie dough. Okay, it's not really cookie dough yet. It's still eggs and Crisco, but eventually it's going to turn into some nice cookie dough. Okay, so it's kind of like when you see all the things mixing up. That's activated complex that we also call transition state. It's not really reactant. It's not really cookie dough yet. It's kind of a mix. Okay, activated complex. The hump, remember, that's activation energy. This is really important. Picture yourself. You're a little runner going over these hills. Which hill would take you the longest to go over? We went over that one real quick. That's a fast reaction because it has a low activation energy. Here's a big one. Oh, that's going to take us a long time. That's the slow reaction because the leading edge is the tallest. It's the slowest reaction. This one's second, and that one, of course, is the fastest. This one's in the middle. So the short humps are the fast reactions. The big humps are the slow reactions. And remember, your rate is mostly determined by the slow reactions. Remember the example of grapes and eggs. So you're eating grapes and eggs for breakfast. The eggs take a long time, you know. You could grab the grapes and you're done, okay? But we have to wait on the eggs. So the thing that takes the longest is the rate-dependent step, the slow step. That's one of our types of reaction mechanisms. The other one involves adding 2 or 3 reactions together. This is a subreaction or an elementary reaction. This is another one. Notice we produce an O here, not O2 or O3, but O1. And then we use an O1 right away. Cross through the O1s. Not the O2s or the O3s. They're different. They look different. Okay? Kind of like a VW Bug looks different from like a school bus. School buses are big. VW Bug's small. An O3 molecule is 3 times as big as an O. So it's different. It is a different molecule. So you find something exactly the same, cross through it. The O and the O. Other than that, you add everything on the left, put it on the left at the bottom, add everything on the right, put it on the right at the bottom. And that would be a reaction mechanism. I also am going to ask you to draw a diagram of these, and I might tell you it's spontaneous, which means that the reactants are higher than the products, or it's non-spontaneous, which means the reactants are lower, and you draw that line like we talked about earlier. And also, if I tell you a reaction's slow, what do we know? The hump is tall, because it takes a long time to go over it. So that finishes up our notes for the second part. Work some of these on the practice problems, work your review, and good luck.